Hi, chemistry students. The last part of the chapter on matter. And we've done quite a bit, I hope. We've done the labs. You've seen matter change, describe the physical and the chemical properties, and hopefully you can describe the difference between a chemical change and a physical change and give lots of examples. Well, now let's talk about classifying matter. So look at my pictures here. We've got distilled water, we've got tea, and I don't know, vegetable soup, minestrone, looks like vegetables. What do they all have in common? Think about it. Yep, they're all made of water. So they all do have something in common. They're all made of matter. And within the matter, we can break down the fact that they all have water in them into water itself, which is a pure substance, or is it a mixture in the case of that soup, a combination of two or more pure substances. If you read the definition, two or more pure substances that retain their own individual properties, and they're physically combined. So you guys should be writing this down on your notes, right? So you notice here the definition again of a substance or a pure substance is when matter is made up of only one kind of atom or molecules. You can really identify it easily, whereas a mixture can be so many different identifiable individual molecules or atoms, and we physically combine them together. Let's try another example here. So looking at a mixture, we can have two types of mixtures. We can have a heterogeneous mixture or a homogeneous mixture. If it's heterogeneous, your book says here that it's one that does not blend smoothly or thoroughly. Well, here's your example. Which one of these two is not really blended very well? Not too hard to decide, right? The muddy water. You can see the mud sitting at the bottom, and then there's a bunch of water on the top. So it's what we consider a heterogeneous mixture. Maybe an ice cream sundae, maybe all types of cereal, and definitely that soup that you saw. Okay, what about the other beaker? The other beaker, you could say, is a homogeneous mixture because it's got a constant composition throughout and it's all in a single phase. This one in particular is a solution. But how do you know it's not just distilled water in the beaker? Think about it. Is it salt water solution? Is it a sugar water solution? Or is it just water? Could you really figure that out? I bet you can, because we did it in class, right? We made a solution, and then what did we do to it? We filtered it out and we boiled it. No filtering here because you don't see any particulates in there. But if you were to evaporate the water away, then you would see that there could be salt or sugar within that beaker. And it's not just distilled water. So that would tell you it is truly a homogeneous mixture. It looks the same throughout, but there's something else in there. Let's try a few more. All right, Kool-Aid. What's Kool-Aid made out of? Basically sugar water. It's another type of a homogeneous mixture. What about concrete? You can see this is a conglomerate of all kinds of different rocks, feldspar and basalt and mica. So that might be a heterogeneous mixture. What about brass? Brass is actually a type of solution, but it's two or more metals that are actually combined. Hamburger? Let's think about it. Every time you take a bite of a hamburger, is it the same? No. So it must be a heterogeneous mixture. Now the sodas are pretty consistent, so you could probably guess they are, that's right, homogeneous. All right, going back to these solutions that are homogeneous mixtures, I don't want you to think they're all salt water or sugar water. You could have a gas and a gas, which is where you're at right now, right? The atmosphere. A gas and a liquid, carbonated beverages, liquids in a liquid, radiator fluid, vinegar, solid in a liquid, you see often, right? All those powders that you dissolve. Or again, like that brass, those alloys, which are solid solutions of metals. Here's a couple more alloys. Do you recognize these? What are your mountain biking wheels made out of? Those are pretty cool, huh? Look at those, no spokes there. So what are they made out of? Probably aluminum. They used to be steel. Now they're aluminum alloys, maybe with some carbon fiber to make them stronger. And what are coins made out of? They are all alloys But a penny might be not just copper on the outside, but maybe zinc on the inside. So again, alloys are solid solutions of two or more metals. Now, if I truly have a mixture, how would I separate it? I'm going to give you some examples here. You write them down. There's a little space on your notes to write them. What are we doing here? Like we did in class, we filtered. So filtration, there's the definition. A technique uses a porous barrier to separate the solid from a liquid. We took salt and sand, you filtered in class, you made a filtrate of a saltwater solution, and then using the Bunsen burners, remember we evaporated the water so you could get the salt back out. So filtration's an easy way to separate a mixture. Distillation, a little bit harder, a technique based on differences in boiling points of substances. Let me give you a picture here. So if I had some different substances in here, which I hope we're going to do next week, we're going to try to distill some alcohol and water and show you what some heating curves are. But here, when we distill, we cool it down. And what's going to happen is we'll end up with a pure substance here. Better example might be fractional distillation. If I take crude oil, if I take crude oil out of the ground, this pure petroleum product, it's very thick, tons of long chains of carbon molecules, and I start to warm them up. Think about it. What type of molecules will rise up in this column? It's going to be the carbons that are very small. Remember those natural gases we talked about in class? Methanol, ethanol, propanol, butanol. This happens to be butanol because they say there's 4 carbons in it. So they'll go to the very top of this fractional distillation tower. We put in a pipe right at that level where we know the carbons will rise to, and then we cool them down. And as we cool them down, then we have some natural gas. You look at the different petroleum products. All these hydrocarbons get heavier and heavier down in the column. If you cross over the Richmond Bridge, you might see some of these towers because Chevron has some plants over there. And at the very top, sometimes you see a flame burning off any materials, so it doesn't go into the environment, but they're fractional distillation towers. So look for pipes on the side that has different degrees of carbon molecules, larger as we go down. And like I said, we'll do a lab in class next week, which will show you this as well, which is kind of cool. Okay, crystallization, another technique to purify a mixture. So we can separate that mixture by allowing the charged particles, in this case they're ions, that might be attracted to one another to crystallize out. So these different ions find each other, and the slower they cool, the larger the crystal they are. Chromatography. Here's a technique that we tried in class last week. This one's a little bit different though because it's separating plant pigments. Here we have chlorophyll B, chlorophyll A, xanthophyll, and carotenes. And they're being drawn across a piece of filter paper or a type of chromatography paper. And this one's probably with an alcohol or an ether solution. In class, we used filter paper and we separated just colored pigments. So let's read the definition. The technique that's used to separate components of a mixture based on the tendency to travel or be drawn across the surface of another material. So the solvents that we use to move across this chromatography paper or filter paper can be different. Who moves the farthest? Well, whatever's attracted to that solvent will really move the farthest. It's not always about density, although you can assume that large molecules may not move very far. In this case of chromatography, when you look at the chromatogram, the one that actually moves the farthest is because it's attracted to the solvent that's moving across that filter paper. All right, let's talk about elements. So we have mixtures made up of identifiable properties of things, or we have pure substances or elements. What's the most common elements in the earth? Here you have oxygen, it's red on red, and silicon. These are a little graphic from your book there. Okay, so now we're on the other side of that chart. We'll come back to that chart too before you leave it, but hopefully you're still filling out your notes. So we have pure substances, which can be an element or a compound. How do we know the difference? Well, the elements, right now there's 118. We've got some new elements down here that were just named in the last couple of years. We'll talk about those a little further. But those are the 118 elements on the periodic table, and they cannot be separated by ordinary means. Here's your textbook definition. Pure substances cannot be separated into simpler substances by physical or chemical means. I say by ordinary physical or chemical means because you could put some of these elements into a cyclotron or a linear particle accelerator, an atom smasher, but we're not talking about that. Basically, going back, there's 118 elements, and it's very difficult to separate those. So that's why we define them as an element. About 95 are occurring naturally off the periodic table. Hydrogen's the lightest. If you look at our periodic table in class, you'll see solid different gases, and they're different colors. And we'll look at that in the class next week. Okay, there's a special kind of element called an allotrope. You recognize these. Oxygen gas. And then what if I have 1, 2, 3 oxygen atoms? It's no longer oxygen, but ozone. Yeah. So what's the definition of an allotrope? There are different molecular forms, 2 oxygens, 3 oxygens, but they're both gases, same physical state. Here's kind of a cool one, carbon. We used to have just a couple different types of carbon, and you know that diamond's a lot stronger bonded than graphite. Notice graphite forms in layers, but under intense pressure and temperature, we can actually tweak those carbon atoms to form diamond. Well, now we also have buckyballs, named after Buckminster Fullerene, and even some very cool graphene, these carbon nanotubes. They're pretty amazing. I'm going to let you watch a video on them. They're not super new, but they've been around a little while. So here's a little YouTube video that's called Why Graphene Hasn't Taken.
It may not look like it, but I'm creating one of the strongest and most versatile materials on Earth, graphene. You've probably heard buzz about it. Graphene made big waves back in 2004, and it's knocked around science news ever since.
A global race for graphene.
You know, it's not just limited to one little thing.
One of the greatest discoveries of the 21st century.
Graphene could be the key to a lot of mind-blowing technology.
But that was almost 15 years ago. Where are all of the graphene wonders that we were promised? The bulletproof armor, the graphene circuitry, the ultralight airplanes, the graphene medicine, a space elevator.
So the next time man walks on the moon, maybe he'll take the elevator to get there.
Clearly, lots of the buzz never went anywhere. But graphene does exist. Engineers have gone from making one fleck at a time to producing it by the barrel full.
Do you want to try to pick it up?
Sure. So the graphene revolution we were promised may already be in motion.
You can stretch and pull on it, and in fact, a good way to visualize it is that if you had a big enough sheet of pure graphene, you could hold up a soccer ball on just one atomic layer, and that's insane.
Joseph Meany is an analytical chemist who co-authored a book about the promise of graphene. He explained to us that graphene is just carbon, like coal or graphite or diamond. The difference is in how the carbon atoms are bonded together, and in the unique shape that the material takes.
So it's just a single atom sheet. There's no Z dimension to speak of in graphene. And these atoms of carbon are arranged in interlocking or tessellated hexagons, kind of like a chicken wire. The bonds between the carbon atoms are actually extremely strong.
Back in 2004, researchers in the UK discovered that they could produce graphene with some shockingly simple tools, a hunk of a particular type of graphite and some standard issue tape.
Yeah, it was just a very large hunk that you could hold in your hand, and they took the tape and put it down onto the surface of the graphite and just lifted it off.
From there, they used chemicals to dissolve away the tape, and they were left with tiny flakes of graphene with remarkable properties. It's impossibly light, yet incredibly strong. It's flexible, and it's a highly efficient conductor of electricity. The researchers won a Nobel Prize in 2010, and today in 2018, literally everything around us is built or enhanced with graphene. Okay, not quite.
I think it's very easy for the media, for the press to seize on any new scientific or technological development as something that's going to be transformative. You know, scientists come up with these amazing new materials and then everything changes, and of course it never really happens that way.
Philip Ball is a reporter who's written a bunch about the graphene hype machine, and I asked him to throw some cold water on the story.
Hello?
Hi, is this Philip Ball?
It is, yes.
Hi, how you doing? This is Corey calling from The Verge.
Hi, hello, Corey. Of course, with any new technology, the reality is it generally takes years to develop it. It would be unreasonable to expect graphene to transform our lives overnight.
The uphill battle for any new material is that it can't just be better than existing technology, it has to be much better. Philip says that's the issue with graphene replacing silicon in electronics.
Certainly there are companies who are exploring its use as a conductive electronic material, but of course we already have such materials, and graphene has really got to have big advantages over what we have already if it's going to displace what is already a well-established, mature technology.
But that's not to say that graphene hasn't gone anywhere in 15 years. We found some engineers who are making materials with graphene today, materials that could one day even end up in spaceships. The company is Vorbeck Materials, and their president, John Leto, showed me how far they've come with graphene mass production. And he gave us a free sample. Literally just like floating in the vial.
And so if you open that up, you can take out, this is a bag of about 1.5 kilograms of graphene fits in a 30-gallon container. So it's very light, sort of very voluminous in its sort of raw state.
Vorbeck is introducing its manufactured graphene powder to all sorts of industrial and consumer products like RFID tags, clothing, and even rubber.
So you take the graphene, you blend it into rubber, and in rubber they use sort of big blenders almost that beat the rubber around, mix the graphene into it, and what you get by mixing the graphene with the rubber is very high temperature capabilities and also very high strength.
Thinking about an application for this, you talk about spaceships, right?
Right.
You're going through extremely high temperature to extremely cold temperature in outer space. You don't want rubber that would expand and contract and lose its strength over time.
Exactly.
This material won't do that.
That's exactly right.
And on the electronics front, Vorbeck has created graphene-based inks that can be printed in mass on standard printing presses. When printed on waterproof fabrics, they can be washed, heated, ironed, wrinkled, and twisted without damaging the circuits. This is extremely promising for the future of graphene-based wearable electronics, which John says we should be on the lookout for in 2019.
What we really hope is that we can walk into a room 5 years from now, and most people in that room will have an article of clothing that has graphene wearable electronics in it.
So there are big things happening with graphene. We just have to be patient, and we can't believe everything we read about it. And for what it's worth, we've been here before.
It's this sort of long-standing notion of a wonder material. I think it does go back to the dawn of the plastic age in the 1920s and 1930s. You know, you saw the same kinds of promises made for them, that they were going to be these, wonder materials that would do everything.
I just want to say one word to you. Just one word.
Yes, sir.
Are you listening?
Yes, I am.
Plastics.
Plastics, they clearly had a huge impact, and they do all kinds of useful things, but they have their limitations too. I guess it was really a sort of reference to this sort of long-standing idea of wonder materials that were, going to solve every problem.
Graphene might not be a wonder material any more than plastic is, but the way John sees it, if graphene works well on its own merits, the hype won't matter at all.
We really don't want our customers to care whether it's graphene or not. What we want them to know is that this device that you're using works better for longer than anything else you can get. And whether it has graphene in it, whether they advertise it and use that hype as part of the marketing or not, is sort of completely irrelevant. It just is better.
Hey everyone, thanks for watching. If you have any...
Did you watch it all the way through? It's okay if you didn't. But that electronic clothing sounds pretty promising. So we'll see what happens with graphene. Will it be like plastic in the future? Time will tell. All right, let's go back to those compounds. So graphene, take a little step back. Graphene, like graphite, like diamonds, like buckyballs, all of them were solid forms of carbon. And so we call them allotropes. So remember, same molecular form, which is solid, but different structures. And so you can see how some of these are very different. All right, so we'll look forward to seeing the effects of graphene. So what if I take two or more of these elements now and I chemically combine them together? Then we get compounds, like, write some examples down if you would. Water, carbon dioxide, hydrogen peroxide, ammonia, that's what's in most of your Windex type cleaners that you clean glassware with, and sugar. We talked about these two ring structures making sucrose when we dehydrated it in class the other day. And this is table salt. We didn't write the formula, but hopefully you know it. NaCl, table salt. So how would you separate compounds? I have water. How would you get rid of water? Now, if you said boil it, that's not going to answer this question, right? When you boil water, it's just steam or water vapor, which is still H2O. The only way to actually separate the hydrogen, right, from the oxygen, want to break that covalent bond right there, is by electrolysis. So with electricity, how would you separate a methane molecule? That's what in our gas jets at school. We burn it, right? Because then you know we get carbon dioxide and water. We've done that one. And I don't know, ammonia. Ammonia is a very strong acid. You could react it with a base and a base with an acid. Or in the lab last week, we took a salt solution, sodium chloride. We reacted it with silver nitrate and we got a precipitate, a completely different chemical, which will separate all these ions from each other and recombine into something new. So how do we separate compounds? We use a chemical means. So go back to your chart in your notes and let's look at this. How do I separate a mixture from into its pure components right here? You can make a little note of it in your notes. We separate a mixture by physically all the ways. A magnet we used in class, and filtering and chromatography and boiling, phase changes, all of that separates mixtures into its pure substances. Okay, now let's go down here. What about how to separate a compound into its elements? We just talked about those, right? All those chemical ways, reacting with acids or bases or combustion or electricity, oxidation, somehow changing this compound enough to break it back into its individual elements. And so you have to do it chemically. Think about how we did it in lab. All right, you still with me? We got a couple definitions and then we are done with this chapter. Two laws I want you to know. Laws of definite proportion. Regardless of the amount, a compound is always composed of the same elements in the same proportion by mass. You can write in that definition. But what does it mean in English? The mass of a compound is equal to the sum of its masses of the elements that make up that compound. Okay, that didn't help. Let me say a better English. You got a little? Yeah, here's about 500 mils. Or a lot. Am I going to keep this faucet running forever? It doesn't matter if I have a little or a lot. Notice the ratio of water molecules, hydrogen to oxygen, doesn't change. I always have 2 hydrogens to 1 oxygen, and the percents do not change. Again, that's the law of definite proportions. Here's another example of sugar. And let's use a quantitative example. Can we mathematically do this? Sure you can. I take the mass of the element, divide it by the mass of the compound. So in the case of water, hydrogen divided by water, or oxygen divided by the mass of water, times 100. And it gives us that percent that we just saw, go back a slide here, that we just saw over there, that percent. So we've got a molar ratio and then we have a percent. So let's talk about some sugar here. Let's say I have 20 grams. I got a spoonful of sugar here, big spoonful of sugar. And I have 8 grams of carbon divided by the mass of that sugar. Gives me 42.20% carbon. We can do the same with hydrogen and the same with oxygen. Feel free to write these down on that last page of your notes if you want. But notice that the next slide is the same. What's different? 20 grams versus a whole bunch of sugar from sugar cane, 500 grams. But I'll toggle back and forth. The percents didn't change. They're both the same. So again, law of definite proportions. You got a little, you got a lot. The proportions of hydrogen and carbon and oxygen did not change. Okay, little twist on this. What about the law of multiple proportions? When you have different compounds that are formed by a combination of the same element, then you might have different masses of one element combined with the same mass of the whole element in a ratio of a small whole numbers. Again, what does this mean? Let me show you a picture. We got sulfur dioxide and sulfur trioxide. So multiple proportions. Our proportions of sulfur and oxygen are different, hence multiple proportions. So we combine them in different ways and we get different molecules. So sulfur dioxide, there's 2 here, oxygens, and sulfur trioxide, 3 oxygens. All right, another example might be water and hydrogen peroxide. 2 distinct compounds. We've got water and hydrogen peroxide, but they both have hydrogen, they both have oxygen. But again, the proportion of hydrogen and oxygen are different. That's what that says in words. But let me show you the pictures, right? H2O, 2 hydrogens and an oxygen. Hydrogen peroxide, H2O2. Again, proportions are different. And that's what this says. We're going to wrap this up. And that's what we need to know in this case on matter under the whole big picture of combustion. So we'll continue to burn things and look how matter changes. And fun lab this week, and then we'll do a quiz or an exam on this. Good job. We're done for now. Bye.